Okay, so now we're going to be discussing binary search algorithm, in which basically we are looking at another way of finding a particular element in a sequence of elements in an array. We have studied one alternate method of searching elements in an array, which is known as linear search. We've studied this in paper 2, and we saw how we have to access each and individual index position in attempt to find a desired element, and either you will find it or you will not find it. So you simply access all of these elements. Now, the thing here is that if your array, now if this is important part, if your array is unsorted, so if your array is unsorted, then linear search is the only way to find a particular element in your array. So that's it. So if you have not you have not previously sorted the array, then you are left with linear search only. However, if there is if your array is sorted, then there's a much faster way to try to find a particular element. Now, this method is known as linear search. So basically what linear search means is that if, say, for example, I have this array right here. If, for example, I have this array and I'm trying to find a particular element. And as you can see here, this array is sorted 6, 7, 8, 9. This array is sorted. So let's just say that if I want to find an element, say I'm trying to find an element 11, which obviously does not exist here. But what binary search does is that it starts off by dividing your array in two parts. So basically, first of all, you find the midpoint of the current array. So as you can see here, the midpoint of my array has the value 8 in it. So obviously, if the element I'm looking for is greater than the midpoint, which it is, there is no point in looking at the array, at the elements before this array. So our focus should lie on the element, the midpoint, and the elements after this midpoint. So what we did is that we reduced the searching effort by half. In linear search, we access each and every element, but in binary search, we first of all establish what is the midpoint of this array. Okay. After we're done establishing the midpoint, we ask another question. Okay, we found the midpoint. Is this midpoint having the element that I'm looking for? So that's the first thing we have to establish. So if I'm looking for example, 11, obviously this midpoint does not have 11 in it. So first question I ask is, the midpoint that I just discovered, does it have the element that I'm looking for? If it does, then great, the algorithm ends. But if it doesn't, the second question I have to ask is, if my element that I'm looking for is either greater than the element stored in my midpoint or lesser than the element stored in my midpoint. If the element I'm looking for is greater than this midpoint element, that means my focus should be lying at the right side of this array, because we are looking at a sorted array. And I will no longer consider this left part as part of my searching process, thereby reducing the size of data through which I will have to access to find my element. However, if the desired element that I'm looking for is smaller than this array element over here, in which case I will focus on the left part of this array and I will ignore the right part altogether. In any case, either I'm focused on the left or I'm focusing on the right, I am eventually reducing the size of my array and thereby reducing the time required to eventually find the element I'm looking for. And that's why it is a much more efficient algorithm compared to linear search, because linear search causes you to access worst case scenarios that you have to access each and every element. And if you have a large array, this is problematic. However, in binary search, you can start accessing the middle point, and then based on the decision of the middle point, either you're moving towards the first part of the array or the last part of the array, and thereby, and okay, by the way, you will be doing that after each iteration. So for example, if I don't, let's say if I have now considered the right part of the array, now this right part will be will be considered as an array on its own. So that's a separate array. It's a smaller array, but it's a separate array. The left part of the array I have forgot. But now the right part of the array is my focus. And this is considered as a separate array on its own. And this smaller array will go through the same process, meaning that I will find the midpoint of this smaller array, compare the element at the midpoint of my new smaller array, and see where it lies based on the element I'm searching for. So either I'll be further shifting towards the right part of this smaller array or the left part of this smaller array. In any case, at each pass of my searching algorithm, at each pass of my searching process, I am eventually making the size of my array smaller and smaller and smaller, thereby narrowing down to the eventual position where the element may or may not reside. And again, there is a great chance that the element I'm looking for example, right here, where I'm looking for 11 in this array, which does not exist. And my array has certain precautions that ensure that if the array is not there, it will give an appropriate prompt or message there. So now let's look at how this algorithm works. So again, just remembering this, that we are working within sorted array. If its array is unsorted, linear search is the only way. So you have two options here. Either you go for linear search, or either you can go towards bubble sort or insertion sort. First sort the array, then go towards binary search. But binary search only works for a sorted array. Okay, so consider that I have this algorithm, or I have this array, which I'm going to call data, and as these elements 1, 2, 3, 4, 5, 6, 7. Now, as you can see here, this is a sorted array, starting from index position 1 all the way to 7. Okay, and of course, I will be using index position 0 here as well. We're going to be finding the value 5, so which does exist in this array. So obviously, this will return the index position where it is. Now we're going to be we're looking for the value 5 in this sorted array. Now these are the steps. Okay, by the way, you see index position 0. How many elements do we have here? 1, 2, 3, 4, 5, 6, 7. We have 7 elements here. And that means the size of the array is 7, starting from index position 0 to 6. So to find element number 5, these are the following steps that will take place. Okay, step number 1. We will begin by finding the mid of the array. So index position 0 plus 6 divided by 2. Okay, by the way, this is div2, div2. As you remember, what div2 does, it returns the whole number part. So if it's, for example, an odd number, the index position, if we're resulting in odd division, we're not going to be using 3.5 or 4.5. We'll be using only the whole number portion as our, desired index position. So don't worry about ever ending up with an odd number. We are using the div function over here. You see here, even here, this is the Python code for div, and in algorithm we're using div over here. So we're only concerned about the whole number portion. Anyway, 0 plus 6 is 6 divided by 2, third. So basically the mid of the array is 0, 1, 2, 3. This is my 0, 1, 2, 3. Fourth, the value with the fourth, value 4 at index position 3. This is my third index position, which holds the value 4. If this is our searched item, which it isn't, by the way. So first question we have to ask, that I just reached the midpoint. Is it that value I'm looking for? No, we're not. This is not the value I'm looking for. I'm looking for 5. So if this is our search item, then we will exit and return the index position from which we found it. So that means position 3. So by the way, if I have found the midpoint and my midpoint contains the element that I'm looking for, I will simply proceed towards returning the mid, finish. But that's not the case here, in which case I will have to do the second comparison. However, in this case, 5 is greater than the midterm. Therefore, 5 will be in the second half of the array. So now we are no longer concerned with this part. In fact, we're not even concerned with this part as well, because we already asked this question, is this my desired element? No, it's not. So that means 5, since it's greater than the midpoint element, the element that I'm looking for is greater than the midpoint element. So that means now I will no longer consider this as part of my sample or my data size. I will focus on this size only, this side only. Okay. Now, however, in which case we will now consider the element after the midpoint. Okay. How do we, first of all, this is important. How do we transition from the complete array to only right part of the array. This is important. As you can see here, my if originally you can see that this is my end of the array and this was my start of the array. Okay, now since I have to transition towards the right part of the array and I'm ignoring the left part of the array altogether, so what that means is that my end remains in the same place. That's okay, there's no change in the end. However, the start of the array is now this position over here, which is actually what? One place ahead of my midpoint. One place ahead of my midpoint. So this is the start of my array over here. So if I am transitioning to the right part of the array, what that means is that my start of the array will become midpoint plus 1, like so, and the end will remain the same. However, if I had transitioned towards the left side of the array, what that would mean is that my start will remain the same. However, my end will become midpoint minus 1. But in this case, we can see here, my end of the array is okay, and my start of the array will become this. So in that case, my start will become now midpoint plus 1. So in which case, we will now consider the element after the midpoint as the start of the array, and the end remains the same because we are focusing on the right side. We will then find the mid of this new array. So basically now we have now a smaller array. This smaller array starts from index position 4 all the way to 5, 6, index position 6. So now we have to find the mid of this smaller array, in which case that's 4 plus 6 divided by 2. So 4 plus 6 is 10, divided by 2 is 5. So index position 5, which has the value 6, is now my mid position. Since now, first of all, I will ask, is this my mid? Is this the element I'm looking for? No, it isn't. No, it isn't. Otherwise, if my algorithm would have ended here. Now, since our search item is now lesser than the midpoint, it means that it lies on the left of the midpoint. So the next question I will ask is that the element I'm looking for, the first question I asked is the midpoint the desired element I'm looking for? No, it's not. Now the second question is it greater than the midpoint? No, it isn't. That means it is lesser than the midpoint. It means that now my focus is on the left of this array. My focus is on the left of this midpoint. So what that means is that the start of the array remains the same. The start of the array remains the same. And what happens is that the end will become one place before the mid. And eventually I'll be pointing toward the same element. My start and my mid will be the same. Okay. Since our search item is now lesser than the midpoint, it means that it lies on the left of the midpoint. In which case our last will be one position before mid, that is position 4. And the start will remain the same, which is also position 4. So now again, do the same thing. Same calculation first, which is 4, last, which is 4, divided by 2, which is also 4. Now my mid of this new smaller array is index position 4. Again, check it. Is index position 4 having the value that I'm looking for? In which case it is. And I will simply return the midpoint, and that's the end of my algorithm. Now let's just say, for example, that this was not also the element that I was looking for. It was not the element. In which case, I will have to move towards the left of this array. If, say, just for example, the element I was looking for, that it was even smaller than this last element in this array. In which case, my start will remain the same and my end will be decremented even further. So that means my end will move one place before the starter. And that is what will cause my algorithm to terminate, because that would mean my array is the element that I'm looking for does not belong in my array. We'll look at that with an example. But first of all, let's check out this was my these are the steps followed by my algorithm. Now let's look at how my pseudocode handles it. Okay, first of all, I have found my this is what the pseudocode looks like. My variable found is assigned with false. My failed. Okay, by the way, if my algorithm does not find the element I'm looking for, it will have, this failed variable will have true in it. So right now I've assigned with the false. The first element is my 0, my mid element is assigned with 0, my last element will be the length of my index entire data minus 1. So basically we're considering index position 0. That's why if I have 7 elements, my sixth place will be length of data is 7 minus 1 is 6. My last element will be 6. Okay, now check this condition out. As long as I have not found it and I have not yet failed. And there's hope that it's probably there, right? As long as these both conditions are false, my loop will keep on going. If either one of these conditions become false, true, and either one, this complete condition will become false, and I will exit this loop. So as long as this condition is true, it means that I have not found it and I have not yet failed. So when I enter the loop, what I do is I will take the first division, first plus last, div2. We just discovered what we do that. That's the first time we divide it. If the data in the mid item is equal to the search item looking for, then find is true. So I will simply exit this condition, and the next time when I check this loop, the next time before starting this iteration, found will have true in it, in which case this will become false, meaning that this entire while condition will become false, and I will exit the loop, and I will simply output if found is equal to true, I will output the midpoint that I found it at. However, if that's not the case, what that means is that this condition is not true. That means I will not become assigned found as true, and I will move on to the else state. Now, this is what's happening here. In the else state, I am basically making a sub array of my entire array. Now that depends on whether the desired element I'm looking for is greater than my midpoint or lesser than my midpoint. Now check this out. If my first element is greater than equal to last. Now, if my first element is greater than equal to last, remember what I said here, that if, let's say I was looking for an element that for some reason is smaller than 5. And 5 was the last element. This is the last element that I can look at. I'm looking for an element that is smaller than 5 and doesn't exist. Now this example obviously is, smaller than 5 is obviously 4 and it's part of the array. Let's just say, for example, it's another array, and I will show you in this way. Now let's say my array is like this. I have 1, I have 2, I have 3, I have 5, 6, 7, and 8. Okay. Now imagine that I'm looking for 4. Okay. So as you can see here, this is my midpoint. Is my element smaller than, is my element the midpoint? No, it's not. I'm looking for 4, by the way. I'm looking for 4, which doesn't exist. Okay, and as you can see here, my start is 0 and my end is at 1, 2, 3, 4. This is at 6 and is at 6. And my mid is right now at, and after this, my mid is at index position 3, which is 5. Okay. Now, is my mid, I calculated the mid. Does my mid have the element I'm looking for? No, I don't. Okay, in which case, is my desired element lesser than my mid? Yes, it is. In which case, start remains the same, and my end becomes mid minus 1. So my end will become 2, and we will have to recalculate the mid. So now, as you can see here, my remaining array is just this part, just this part. So as you can see here, I will ignore this entire array. In fact, I'll delete it. So this is my remaining array. My mid end is at 2 and my start is at 0. I will proceed towards recalculating my mid. So 0 plus 2 divided by 1, my mid is 1. So now at the mid of my element is 2. Is mid the element I'm looking for? No, it isn't. So again, condition false. Now I have to ask the question, is it lesser than my mid? No, it isn't. Is it greater than my mid? Yes, it is. So in which case my end will remain the same and my start will move one place ahead. So in this case, my start will move to mid plus one. So mid is at one, my start is now at two. So basically my start and end are both at two. So this is my entire array. This is my entire array, just three. So now calculating the mid again, 2 plus 2, 4 divided by 2, 2 mid is also 2. Okay, now, is the mid the data I'm looking for? No, it isn't. So that condition fails. Is the data I'm looking for greater than my mid? Yes, it is. In which case, what I will do is now, my end will remain the same. My end will remain the same, but my start will become 3. And this is why my condition will fail. As you can see here, this condition over here, is the first greater and equal to the last? Is, by the way, we called it start here, but is the first greater and equal to the last? Is my start greater and equal to last? Yes, it is. Is my start, which is 3, or first, in this case it's called first over here, and our example we call it start. Now, is my start, which is 3, greater than my last, which is 2? Yes, it is. In which case we have failed. And as you can see here, we were supposed to fail because we were looking for an element that does not exist in an array. So that's why this condition is written over here. That is my start greater than my, sorry, is my first greater than my last? And in whichever way you see it, if you're looking at the right side of the array, whatever way you see it, this is the condition that you will meet if you're looking for an element that does not exist. Okay, now moving on. So if this condition has become true, as we just saw an example, if this condition has become true, then our failed will become true. And when I exit this loop here and I recheck for the next iteration, this statement will become false because this entire condition will become false, and I will exit this loop right here. And if this, which is not the case here because I came out of the loop because of this being true, this will no longer be true, and I will simply print item not found. Okay, however, if this is not the case and there is still hope to be, the element exists, I will do what? I will simply compare the data at my mid position. If my data at mid position is greater than my search item, and what I do is that I will move from my, if my data in mid position is greater than my search item, then what I will do is that I will simply move my last, if my mid position is greater than my search item, that means that the array exists at the left part of the array, in which case my last will become mid minus 1. And if this is not the case, that means my desired element lies on the right side of the array, in which my first will become mid plus 1 and my end does not stay the same. And my end stays the same. As you can see here, if this condition is true, my last changes, but my first remains the same. My first remains the same. In this condition, my first, is changing, but my last does not change. So this is either case, this, if either one of these conditions is true, this is the step will be taken. And then further comparisons, further divisions, eventually, if element is found, that means this condition will have been true. And if the element has not found, that means this condition has been true. In either case, you will exit this while loop, either because this becoming true or this becoming true. When you exit the loop, you will ask the question, did I come out because of found being true? In which case you will output the mid position at which I found the array. And else, if that's not the case, then I'll print item not found. That means if this condition is running, that means I came out of the loop because of this condition becoming true. So similarly, as you can see here, the Python code for this algorithm is pretty much the same. This is my this is the data array I'm looking for. We have assigned the flags found and failed with false, assigned first and mid with 0. The last element is the, since we're conditioning the expression 0, The length of the array will be 7, but my last element will be index position 6. Length 7 minus 1, 6. I will take inputs, an integer input of what you are looking for in search item, while found is equal to false and failed is equal to false. My loop will keep on going. This is how I take the div. This is how I take the div of my first plus last div 2 is equal to mid. If data mid is equal to search item, then found true, I will exit the loop. And this, if I exit the loop, I will ask this question and I will simply output the midpoint. So basically the desired index position where the data will have been is basically the midpoint. So we have narrowed down the search until we reach the midpoint where the data might be. And if it is found, we're simply outputting the midpoint. However, if that's not the case, we will do this comparison. If this is true, that means the element does not exist, in which case failed has become true. Exact same syntax, and I will exit the loop. Otherwise, I will narrow down my array by first doing this comparison. And if I have to move towards the first part of the array, I will do this. If I move towards the end part of the array, then I will move this, so on and so forth. So as you can see here, there is not much difference with pseudocode versus Python code, and translation should be rather easy. And this is an example of what the shell has been output. So for example, if I'm looking for element number 5, so 5 is at 0, 1, 2, 3, 0, 1, 2, 3, fourth position. So as you can see here, if I take an input of 5 being the search item, it returns value 4 as the position where it should be. If I'm looking for 9, which does not exist, it will simply output item not found. So the code is working just fine.